Hello all, this is Sumit sir, and today we are going to discuss a code on AlexNet and a code on Inception version 4. Both these codes are available on GitHub. All the links for the code are provided in the link below. I do not own this code. This code is written by the authors of this code. I'm just going to review this code. Now let's get started into the AlexNet code. So first we are going to import all the necessary modules we need. So we are going to import TensorFlow STF. We are going to use TensorFlow in this code. Then we are going to start with the flags. So flags is equal to none. This is just done to initialize the global constant. Then we are going to define a function. I will get to this function a bit later. We'll first start with the inference function. So define inference images. This images is basically the input to our AlexNet. To those who all don't know, AlexNet basically is used to classify one image out of 1,000 classes. So that is like there are 1,000 classes at the output, and we are given just one image at the input, and we are trying to classify that image into the correct class. So and AlexNet was designed in 2012. So coming back to the code, inference images. So if this image is basically the input. In AlexNet, there will be three types of layers. The first one is the convolution layers. There will be 6 convolution layers. Then there will be pooling layers. There will be 3 of those, and the local response normalization. It's not actually a layer. I will tell you about it a bit later, but there will be 2 of those. Now we'll start with the first convolution, that is the this part of the code, this part. So the with tf function just labels our code in this part under the conv1. Then the kernel is equal to tf dot variable. This is just generating a variable with the name as a name kernel. The variable is generated as follows: tf truncated normal with certain dimensions. So we are basically generating a variable with 4 dimensions of 11 by 11 by 3 and 6, 11, 11, 3 and 64. The 11 and 11 are basically the dimensions of our filter. 3 is the number of output channels, and 64 is basically the number of filters that we are going to use. We are using truncated normal so that we can control the standard deviation of our variable. So as you can see, we have noted the standard deviation as 1e minus 1. In the next stage, we will perform the convolution. So convolution is basically combining the input image with the kernel image to obtain a feature map. So the function to do that is tf.nn.conv2d. The images is the input. Kernel is what we have defined over here. This is basically telling us the stride. So we have a stride of 4 by 4. If you don't know what stride is or want to understand more, you can always look into my videos on CNN. Then there is padding, and we are keeping the padding as same. So the output feature map will have the same dimension of the input image. Then we are going to define biases as a variable, and the number of biases should be equal to the number of filters. So we have defined the shape is equal to 64, which is equal to this number of filters. We have also defined that the biases are trainable, so they can be changed. Then the bias variable is basically we now need to add our output of the convolution with the biases that we have defined. So it is given by this formula, which is bias add. So we'll add the output of the convolution with the biases to get this. After adding the biases, we need to perform the nonlinear activation or apply certain non-linearity to our CNN. So we are in AlexNet, they have used ReLU nonlinearity. So the code for that is tf.nn.relu, and in parameters for it are the bias which we have obtained from the convolution, and name is just the scope. So after getting the conv one, that is this one, that is our output of the first convolution layer. We will just need to see what exactly is the output of the first convolution layer. So we are using this print activation function. This basically is calling the print activation function. It just prints the shape of the convolution. So that's the first convolution layer. After the convolution, we need to perform certain normalizations. So AlexNet is basically a 2012 invention, and we have come a long way in terms of normalization, that is batch normalization. But while performing AlexNet, they had performed local response normalization, which is given, which is whose syntax is like this. So LRN is basically used to create higher contrast in the activation map. It is particularly useful when we are using activation functions like ReLU, which are unbounded in nature. Certain functions like tan-h are completely bounded between -1 and 1, whereas ReLU basically allows the output layer to be unconstrained, and it can grow as much as the training allows it to. So local response normalization will control that growth and will keep it bounded kind of. So after the local response normalization, we move on to the pooling layer. That is the first pooling layer. We will be performing max pooling, and the max pooling will be performed on the output of the LRN. So the output of the LRN will basically act like the as the input to the pooling layer. So the syntax for pooling is basically tf.nn max pool. We will choose the image, choose the input as the LRN1, and then we will define the kernel size. Now the kernel size is taken as 3 by 3 and strides 2, and padding is equal to valid. So there will be dimensionality reduction when we perform this operation, and after this we will just print the activations of the pool. After performing the first activation, first pooling activation, we will perform the second convolution layer. I had just run the program, and you can see that we get the shapes of the our output over here. So this is the output of the first convolution. This is the output of the second convolution, of the first pooling. Sorry. As you can see, there is a dimensionality reduction. The 56 by 56 matrix has been converted into 27 by 27. This is because of the valid command in the padding. So the second convolution. Now the second convolution layer will basically be the same as the first convolution layer, just that we will change the kernel size and the number of filters. Now firstly we had used an 11 by 11 size kernel. Now such a big filter is not really required because our input is now a 27 by 27 matrix. So we are going to use a 5 by 5 kernel, and we are going to use 192 filters. Sorry. After defining the kernel, we are going to calculate the convolution or the feature map dimensions. So this, it will have the same command, just that the input this time, instead of the images which was the original input, will be the output of the pooling layer, which is pool 1. Then we will convolve it with kernel, have a certain stride of 1 by 1, and we'll keep the padding same. We'll again define biases, add the bias to the convolution, and then we will apply the non-linearity to get the output of the convolution layer 2. The convolution layer 2 is of this size, as you can see on the right hand side, and you can see the size of the image remains 27 by 27. This is because of the same command in the padding. Next, we will perform the local response normalization that we had performed in the previous part as well, and the output of that part will be the input to the pooling layer, which is the second max pooling layer, and we will again use the padding as valid, and thus our size of the image will decrease from 27 by 27 to 13 by 13. So up till now we have been using convolution 1, then layer LRN1, then pool 1, then convolution 2, LRN2, pool 2. Moving on, we don't require the pooling layer for the next 3 convolutions, and there is no need for LRN anymore. So we just need to manipulate the kernel size of the convolution layers. So in convolution layer 3, we'll just change the kernel size to 3 by 3. This is again because our input has changed from 27 to 13, so we will just decrease the size of the filter from 5 to 3. And we will use the number of filters as 384. Then in convolution 4, we will just change the number of filters and just go on doing the same thing again and again, like the convolution, then define the biases, add the bias, apply the activation function, and print the output. And finally, we will get 128 by 13 by 13 by 256. That is the output of the convolution layer 5. That is over here. After that, we will perform the final max pooling operation. So the final max pooling operation, we will again do a padding with valid. So again, the image will go under dimension, will reduce in dimensions. So 13 by 13 becomes 6 by, oops. So 13 by 13 becomes 6 by 6 over here. Okay. Yeah. So the output of the padding pool layer, that is pool 5, is basically our output of the convolution stage in the CNN, and we are going to use this to so this is basically our output, as I can say. I will just go into a detail a bit later. Yeah, so we will define a run benchmark. This will have the image size. Now the image size is 224. We will define a variable images. This variable images is going to be used later, and this variable will contain the batch size, the image size, and standard deviation. After that, we will call this command. So here we are basically calling the inference layer or the inference function. So by calling the inference function, we are basically calling the entire AlexNet process, which is this whole thing. up to the pool 5 part, up till here. Yeah. So we'll be calling the inference function, and we will get the outputs as pool 5 and parameters, because we are basically returning pool 5 and parameters after performing this function. So those outputs are going to be stored in this. Okay. Then we will initialize a global variable and run this session. So when we run this session, we will go on to this portion. So this is time underscore TensorFlow underscore run. So this is basically another function. So that's this function. Here the parameters are session, target, and the information string. Over here we are going to put the session as ses. That is this total the session. Then target is basically the pool 5, that is the desired output, and this is forward process. So what will happen is we will perform this function, this section. So here we will just mention what the number of steps that we need to take. We'll initialize the total duration squared. Then we'll go into the for loop and then start the time, where start time is equal to time. We will run the session to achieve our target, and then we will calculate the duration. This duration will be the current time minus the start time. This process will go on till I is not greater than the number of steps, and if it is greater, then we will calculate the mean, variance, and the standard deviation. As you can see, it is getting printed over here. It is printing duration, the step number, and the start time and everything. Okay, this is just the forward pass. After the forward pass, we will calculate the error, because that's how neural networks work. We will calculate the output of an input image. We'll compare it with the training set, and if it is comparable, then we will, if it is not correct, then we will calculate the error, and then that we will try to decrease the error. So here we'll calculate the error by the L2 loss command, and then after the calculating the error, we will calculate the gradient, and this gradient is calculated from the error and the parameters that are stated. So after calculating the gradient, we will use this gradient as a target instead of the pool 5 as the target, and do a forward backward pass. And that's how this entire process is run. So AlexNet coding, basically. This is our main function, which will have run benchmark as its input, as a command over here. So how the code will work is, we will start with the main function. It will call the run benchmark command, run underscore benchmark. So run underscore benchmark will be this one. It will take the input size, it will take the image, then it will call the inference, which is our AlexNet crux, which is this part, this inference. And finally, then we will call the time TensorFlow run command, just to calculate the error in our network, and then rectify the error by a backward pass. This part over here is basically to determine the batch size of our input and the total number of batches of our input. And that's it, I guess, for the AlexNet code. Thank you for listening to this code. I hope you understood everything. I have tried my best in explaining this. and you can always visit the link to have a better understanding on this code, and you may as well try this code on your own laptop. Thank you. So that was AlexNet. Now we will continue towards the Inception V4 code. Now this code is also taken from GitHub, and all I do not own anything. It is all on GitHub. You can refer to get that to the link that I have shared in the description, and you can go towards copy this code and try it yourself. I am just going to do a code review on the Inception V4 code. So let's, what is inception module actually? It is just, instead of choosing a particular type of convolution at a time, we will combine all the multiple convolution, that is a 3 by 3, 5 by 5 and a 1 by 1, along with the max pooling together and concatenate it. So it may sound a little confusing, but it is actually really easy, and it is beneficial in terms of the amount of parameters that are required uh, co- to code this. Basically, it is better and more efficient than AlexNet. So let's get started. This is the import part. We will import all the necessary modules and libraries that we require. This part I will come back later. Okay, let's start with the convolution block. So we have defined a convolution block with a certain number of parameters as x, which is basically the input. This part is the number of filters. This one is the number of rows in the filter, number of columns in the filter. This is border mode, equal to same. Border mode basically acts similar to the way padding does in AlexNet, and subsample is very similar to what stride does in AlexNet. Also, this is basically the default values. So unless specified, these are going to remain the same. Okay, the first part, if k image dim ordering is equal to d. So what does this mean? This is basically, we are checking whether the ordering of the dimension of the image is in Theano or in TensorFlow, because in Theano the channel is mentioned on the second index, or that is, on the first, on index 1, first being index 0, second being index 1. So it is mentioned on the index 1, while in TensorFlow it is mentioned on the index 3, in 0 1 2 3, that is the fourth one. Okay, so that's why we first check whether the dimensioning is in th, that is in Theano or not. And if it is in Theano, we will specify that the channel axis is 1, indicating the index number. And if it is not, then we will mention the channel axis as -1. This is basically going reverse. So 0 and -1 becomes 4, kind of thing. Okay. So the first part of the convolution block is to perform the convolution in 2D. So we'll take the number of filters, the kernel, the stride, that is the subsample, the border mode, and the bias. We will perform the batch normalization. So batch normalization is performed to increase the stability of the neural network. Batch normalization normalizes the output of the previous activation layer. So basically it doesn't allow the output to vary drastically. It's similar to what LRN does. After that, we will do the ReLU activation. This is basically applying the non-linearity, and then we will return x. This x is basically this one that we get after the activation. So once we call this block, we get the output as x, which is the output after the activation or after the ReLU. Okay, so Inception V4 has basically three major parts. First one is the Inception stem. then there are 3 inception blocks and 2 reduction blocks. So we are going to first define what is inside the inception stem, or how the inception stem is formed. So this is the inception stem function, and we are going to check again whether it is a Theano or TensorFlow. By this is going to be used everywhere almost, so this is like a common block, you can say. Then we know that our input image is going to be a 299 by 299 by 3 image. It can also be a 3 by 299 by 299, but it's kind of similar. I am going to consider 299 by 299 by 3 in this particular explanation. Border mode equal to valid, this basically implies that there is a reduction of dimension of the input. So if the border mode is unspecified, the border mode is same, which implies there is no reduction in the dimension. And the default subsample size is 1 comma 1. So unless specified, it is always going to be 1 comma 1. Okay, before going into the exact coding of the inception stem, because this is really difficult to understand without the help of a block diagram, I'm just going to pull out the block diagram from over here. Okay, so this is the inception stem block diagram. This filter, concatenate and all, it starts from bottom. So we have our input, and then we go perform the convolutions, and this is how basically the flowchart works. So I am going to go from the code to the block diagram often, that is from changing from here to there, so I hope you don't get confused. Okay, so in the first 3 parts lines of the code have the x variables. So in the first part is the convolution block, input 3233, subsample given as 2 comma 2, and border mode is written as valid. So that's basically the first convolution that we are going to perform. You can see in the flowchart that is the 3 by 3 convolution, 32 side 2v. This v implies valid. Okay, the code and the flowchart are basically the same thing. As I go down the code, I will go up the flowchart. The next part is basically to do another convolution with a 3 by 3 filter, this time with 32 filters and valid border mode. So this 32 over here in the third last block, the 3 by 3 convolution part, this 32 implies the number of filters. These numbers in the brackets actually imply the number of filters. This. So that's a general notation that has been used in Inception V4. So we will perform the 3 convolutions to get over here. Okay, so we get over there and we find this x. After that, we are going to do 2 convolutions on the two convolutions, I would say, on this image. So we are going to do a max pooling on one side and a convolution block on the another side. So this x1 over here we are going to perform max pooling, x2 over here we are going to perform convolution block. Then we are going to concatenate it. Concatenate it is basically means combining them, merging them. So the dimensions remain the same, just that the number of filters increase. Okay, and then we get the concatenated output. After concatenation, we are again going to split, and then again going to concatenate, again split, again concatenate. That is the basic flow chart of this IPv4. I'm going to just minimize this flow chart and just go into the code. I hope you have a slight understanding of this flow chart. If not, you can open this flow chart in your own file, in your own laptop. The link for the flowchart will be given in the description. It is also this particular link over here. Okay, so where I was, here. So I have merged the first block, then I will again bifurcate or split. So I will split into x1 and x2. The x1 will have two convolution blocks, and the x2 will have four convolution blocks. As you can see, x1 will have two convolution blocks, x2 will have four convolution blocks, and then they will concatenate. The only changes inside this are basically the filter size and the number of filters. Another important notation here is this 1 by 7 and 7 by 1. Now, why did we do this? Why not just take a 7 by 7 filter? Well, when we do a 1 by 1 and then a 7 by when we do a 1 by 7 and then a 7 by 1, we just perform total 14 operations. 7 operations over here and 7 operations over here. Whereas if we perform a 7 by 7 convolution, we are going to perform a 49 operations for the convolution. So this is basically optimizing the code. Okay, then the x1 and x2 are then again merged over here, which is this part. Finally, we are going to again split into x1 and x2. One part will do the convolution block and another will do the max pooling, and we will again merge. The final output for an image shape of 299 after going through this entire process of inception stem will have this dimension, a 35 by 35 by 384. 35 by 35 indicate the height and the width. 384 is basically the depth of the image, or you can say the number of filters that are going to be. Oh yeah, you can just call it the depth of the image. After the inception stem, we are going to perform the inception A layer, and this layer is going to be performed 4 times. So I'm just going to the create inception function. As you can see over here, we are going to we are going to perform inception A for 4 times, inception B for 7 times, and inception C for 3 times. So that's how it is going to go. Okay, so inception A. I will just pull out the block diagram over here. So this is inception A. We have a filter concat, that is the output of our inception stem. We will then split it into 4 parts: A1, A2, A3 and A4. The A1 part will just be the 1 by 1 convolution with 96 filters. The A2 part is going to be the 2 convolution blocks, that is this one. It will first go to 1 by 1 and then a 3 by 3 to the filter concatenation. Now you may ask, why not just do a 3 by 3 rather than a 1 by 1 in the middle? So the answer to that is basically optimization. If we do a 3 by 3 directly, there will be more number of computations. If we do 1 by 1 and then 3 by 3, there will be less computations. Thus we do this. There was a figure here, I don't exactly remember, but if we do a 5 by 5 convolution directly, we will require 20 million or something operations for a huge image, whereas for the same size of image, we will require around 2.4 million if we do the 1 by 1 prior to doing the 5 by 5. So here it is a 3 by 3. So a 1 by 1 followed by a 3 by 3. This is done for optimization purposes. Even here 1 by 1 is done for optimization purposes. This is basically the A3 block. So we'll do 3 convolutions. In the A4 block, we will do the average pooling. You may not know the average pooling. What is average pooling? So it's basically, it's similar to max pooling, but instead of taking the average, instead of taking the maximum of the specified pixels, you are going to take the average of all those pixels. So that is going to be done in A4 block. After performing A1, A2, A3 and A4, we are just going to combine them and merge them to give us one single output. That is inception A. This process is going to be continued in a loop. So this one is going to fed back over here and over again and again for 4 times. Finally, after 4 operations, we are going to get an image of the same size, which is 35 by 35 by 384. Now, why is that so? Why is there no dimensionality reduction? As you can see, nowhere over here the border mode is specified. As I mentioned earlier, border mode basically means the padding. So, except over here, but here border mode is written as same. When we call the convolution block, that is this part, if border mode is not specified, border mode is going to remain same, and thus there will be no dimensionality reduction. And thus even after 4 inception A layers, we are going to have an image of the same size, just so there will be no dimensionality reduction. After inception A, we are going to do a reduction A part. So the reduction A part is over here. So in reduction A, we will again check the Theano. This is basically common everywhere. We have to check whether it is Theano or TensorFlow. Then we are going to split our output of inception A into 3 parts. That is the R1, R2 and R3. R1 will just have a convolution block. R2 will be the 3 convolution blocks. Again, the 1 by 1 over here is for optimization purposes. And then a 3 by 3 max pool will be the R3 block. The stride to over here, and over here will reduce the dimensionality, and also because the border mode is valid in reduction A procedure. Thus, our input image will reduce from the size of 35 by 35 to a 17 by 17 by 1024 image. This 1024 is basically addition of the last values of the filter. It is basically 384 plus 256 plus sorry plus however filters there were used over here. Yeah. Okay. Then lastly, so that was A part. After the A part, we will move on to the inception B part. So the output of the reduction A is going to be fed into the inception B part as input. So I'll just pull out the block diagram of inception B over here. So this is inception B. So this part is the output of the reduction A. The B layer is also like A layer, split into 4 parts: B1, B2, B3, B4. B1 will be just the 1 by 1 convolution. B2 will be the 1 by 1 convolution followed by a 7 by 7, but the 7 by 7 is done like a 1 by 7 and a 7 by 1. There's a small typo over here. It should be 1 by 7 and a 7 by 1. And over here we will again go 1 by 7, 1 by 1, 1 by 7, 1 by 7 by 1, 1 by 7, 7 by 1, and 2 filter concatenation. So this procedure is pretty similar. We just need to know how a convolution is going to be done and what is average pooling and how it is also achieved, and then we're just going to merge it all. So the output of the inception B is basically going to be of the size 17 by 17 by 1024, which is the size of the reduction A output. So after finishing the inception B layer, we are going to reduce that layer. We want to reduce the dimensionality. So we are going to introduce another function called the reduction B function. So for the reduction B, this is the flowchart. It is like reduction is split into three parts. One part will be doing the convolution over here, 1 by 1, 3 by 3. The another will be doing convolution over here, 1 by 1, 1 by 7, 7 by 1 and 3 by 3. And the last one will be the max pooling with the 3 by 3 filter. The stride 2V over here reduces the dimensionality of our image. So the output of reduction B is going to be a 8 by 8 image. From 17 by 17 we go to the 8 by 8 image. This output of reduction B is going to be fed into inception C. Now, as you must have guessed, inception C will also be similar to inception A and B. A filter concatenation, which is this is the output of reduction B, is going to be split into four parts: C1, C2, C3, C4. C1 will be just the convolution, C2 will be the this part, convolution, then splitting, then again merging. C3 is going to be convolution, 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 again splitting, again merging, and C4 will be averaging, and then all those to come together to be concatenated. So output of inception C is going to be an 8 by 8 image. Okay. Now we are now done with the inception stage of the inception V4 architecture. We will now go into the main block, which is the create inception block. So how it goes: first we'll check Theano or not. We will get X as the we will first check Theano, then we will take the input. After getting the input, we will call the inception stem. Inception stem will give us some output. After getting the output from inception stem, we'll call inception A 4 times, followed by a reduction procedure of reduction A. Then we will call inception B 7 times, followed by a reduction B. Then we'll call inception C 3 times. After finishing inception C, we will finally need a 1 by 1 image. So to do that reduction, we will do average pooling with a 8 by 8 filter. And doing this average pooling will give us a 1 by 1 by 1536 image. We will then perform dropout operation. Dropout operation is basically done to avoid overfitting, and then we will flatten out the image. So this 1 by 1 by 1536 will now become just a vector of 1536. Now we know that there are 1000 outputs or 1001 outputs, 1001 classes. So the number of outputs is basically the number of classes. So the output is going to be calculated as follows. So dens basically calculates the output, dens command, and it takes the parameters as output, that is the number of classes and what kind of activation we are going to use and what is the kind of input that we are giving. So x equal to flatten x will give us some output x. This output x will act as an input to the dens function, and we know the output to be the number of classes, that is 1001 classes, sorry, and the activation is going to be a softmax activation. After getting our output, we will form a model. So the model is just going to be the input, output, and the name of the model that we are creating. So input is our init, which is this one, followed by output, which is this, and then the name inception V4. Okay, so now we have found out the model, but how do we design the weights of the dense network that we are going to create? So for getting the weights, we should check whether the weights are preloaded or not. So in the create inception, there are two parameters, that is the number of classes and load weights. So here load weights is true, so that is we need to load the weights. So here is how we load the weights. So if load weights is true, we will check whether the backend is Theano or not. If it is Theano, we will check whether the ordering is Theano or not, image ordering, dimension ordering. And if it is correct, that it is Theano, then we are going to use this line to get the weights. So this portion is basically what was at the start. This basically points to the repository of the weights, and we are going to call that function. If the image ordering is not th but the backend is Theano, we are going to use this part. And if the backend is not at all Theano, then we are going to do this portion. We'll again check whether the ordering is Theano or not. If it is, we'll take this for the getting the weights. If it isn't, we'll do this. Finally, after performing this if else loop operations, we are going to get the weights value. These weights value should be stored or should be given to our model. So we'll give it like this: model dot load weights brackets weights. So this weights is basically the weights that we get, and then we'll print that the weights have been loaded, or the model weights loaded, just to tell us that yes, the model is ready. And after that we will return the model. Okay, so for that we will need to go into the main function. So this is the main function. We'll just type create inception v4 with load weights equal to true. So here there is a number of classes is not specified, so we'll consider the number of classes to be 1001, and load weights is given as true. So we will just perform this operation. This operation is pretty easy to explain. Like just go through the entire process. Like take the input, call the inception stage, call the inception A 4 times, call reduction A, call inception B 7 times, call reduction B, inception C, followed by average pooling, dropout and flattening, then calculating the output using softmax activation, then creating the model, and finally loading the weights. So that's all for this video, and I think it was a pretty good video on AlexNet and Inception v4's code in general. I think I have explained it well. I have tried to explain it well. I hope I haven't messed up anywhere. I think I have not. So that's it. I will follow this by the references to all the codes and everything. These are the references for the AlexNet and the Inception v4 coding video. The GitHub files are the files I have reviewed the code from. The Inception v4 file is the first reference from T2 1994, and the AlexNet benchmark file is from the TensorFlow models. The link for the images is the link for the paper of Inception v4 is the third link, and the other links are just for the links that are needed for the understanding of the code. Thank you so much for the patience.